Hello, everyone. Welcome to our break-free lunch and learn webinar series. I'm your host, Laura with Videre Creative, and today's episode is all about compressive versus flexural strength, why compressive strength is the better choice for concrete. And for anyone new to Wavelogix, here's some background info. Founded in 2021, Wavelogix partnered with the Indiana Department of Transportation and Purdue University to enhance road and bridge reliability while minimizing traffic disruptions. Our patented Rebel concrete strength sensing system offers real-time in-place concrete measurements, streamlining project schedules and reducing costs. Our speaker, Joe Turek, is a seasoned engineer with a SEE from Notre Dame and an MBA from Northwestern. He holds 5 patents in microwave telecommunications technology and is a registered professional engineer. Once again, if you want to leave any questions, if you have any questions to ask during the webinar, you can use the Q&A function below and we will answer all questions at the end. Now I'll hand it over to our presenter, Joe Turek.
Thanks, Laura. I appreciate it. Welcome, everybody, to our fourth in the series of 5 webinars and our Lunch and Learns. Hopefully, you'll enjoy today's presentation. We have some exciting news in Chicago where I'm based. We had our first snow today. I'm looking out the window, seeing about 1.5 inches of snow so far. So no concrete will be poured today. I'm also wearing my Rebel Red colors scheme today, so that should be kind of fun. Anyways, let's get this road on the show. Why is knowing concrete strength really critical in our business? And it's critical because there's a lot of operations that we do when we need to know the strength, such as removing forms from the concrete structure, removing scaffolding when you're building floors in garages and buildings. Post-tensioning cables in bridges and decks have to be done at a kind of a precise strength. Releasing traffic, the DOTs and anyone in the county construction of horizontal roads want to get traffic moving as fast as possible, along with all of us sitting in our cars in traffic. So that's important. Segment pouring, if you're pouring columns and walls, you pour them sequentially. As the concrete dries and hardens, then you can pour more. So knowing that strength of when you could pour onto the next section is really important, because if it's too weak, the wall is going to collapse. Panel lifting, if you do tilt-up type of work, or even other types of work like in precast, if it's not cured enough and you go to move the wall, you move the precast, it'll fall apart. And finally, in a lot of cases, payment is paid once you reach the specified strength. So strength is really important. And when we get it wrong, bad things happen. Like the Hard Rock Cafe collapsing in 2019 and bridge collapsing in Pittsburgh in 2022. So concrete can collapse if it's not properly put in place. So what's been our method for measuring strength? As I like to call it, Breaking Bad, if anyone followed the series. It's a 100-year-old technology. And we've basically had at our disposal really only 2 methods of checking for strength. Either cylinder testing or beam testing in a compression method where we break them to determine what the strength of the concrete is at that time. And then we base our decisions around those breaks. And depending on which one we use, whether we're using beams or we're using cylinders, is often driven by cost and availability of the technology at that time. And if you pick the wrong choice, ultimately it could lead to higher costs. In a lot of areas that are using low carbon concrete or beam methods, if the beam fails and doesn't reach specification, then you end up having to go to a core sample of the structure. And that's expensive, time consuming, sometimes hard to do. And so you want to make sure you pick the right technology if you're going to be using compression breaks. And while you thought maybe the choice that you made was the right one at the time, if you pick the wrong one, then that could really lead to disruptions in efficiency, especially if you have to do something like a core sample. So picking the right type of technology for strength is always important, especially if you're bound to be using compression or cylinder breaking. Just to be clear, when we talk about compression brake, what are we talking about? It's pretty straightforward technology. At the time that you're pouring the structure, road, bridge, building, whatever, you pour some companion cylinders in cylinder braking, and they're usually in a cylinder that's a standard 4 inches in diameter by 8 inches tall. We used to pour, and not so often, 6-inch diameter, 12 inches tall. It's basically a 2-to-1 ratio. We pour that cylinder, we cure it, and then we press it in a hydraulic press. And the hydraulic press presses a plate against the ends of the cylinder until it finds its weakest point, and then it shatters. And that's usually when you're shattering the difference between the cement that's holding the aggregate together. And that's just simply exactly what we're describing. We are compressing the cylinder to its breaking point. Compare that to a flexural beam brake. It's exactly as it sounds. A beam is produced, and usually it's produced in the size of a 6 by 6 inch square or rectangle that's 20 to 24 inches long. And then that's pressed in a 3-point press, 2 in the end and 1 in the middle. And as you can see in the graphic, it kind of presses it down until it reaches its point of deformation, a lot of times called the modulus of rupture. And, again, we're finding the weakest point where the beam deforms. In this particular test, rather than measuring compression of the concrete, we're measuring its tensile strength, where it really bends in tension. So when to use one over the other? Some of the reasons for doing that. Well, of course, the first one is if it's required by your specification. Several DOTs in the country require flex beams for final certification of strength. So if it's required, then you end up using it. But a lot of times it's used when the structure itself is going to be under tension, most obviously in bridges and in tilt-up panels, anywhere where you have non-reinforcement underneath the concrete structure, where it might see flexural tension or pressure. And usually it's preferred only for final strength measurements. It's not really done for interim steps like compression brakes are done. In comparison, compression brakes using cylinders are ideal if you want to create a time versus strength curve. And then we end up doing periodic breaks along the time to see what early strength looks like. So if you're doing early strength, commonly you would use cylinder compression testing. And if you're doing final strength, you would use beam, specifically if it's in something that's going to be under tension. Most commonly today, cylinder brakes are used in the industry. And why? Well, if you look at some of the disadvantages of flexural testing, for one, the flexural strength of concrete is about 1/10 the compressive strength of concrete. So that's the unique thing about concrete. It's very strong in compression, but very weak in tensile strength. It's one of the reasons why if you have something that's going to put the structure in tension, you put a lot of rebar in it, because the X and Y direction is horrible in concrete, about 1/10. So if you had a 4,000 PSI structure of concrete in compression, that's going to be equivalent to about 400 PSI in flexural strength. And those variances result in detecting flaws a lot more challenging. So if you have a small little break and your method of measuring is only 1/10 that of the other method, so 400 PSI compared to 4,000 PSI, if you have a 10% variation in 4,000, that's 400. if you have, you're going to have very small tolerance for variation in Flexural. And it's very heavily reliant on proper sample preparation. So if that sample isn't prepared right, it's more apt to have some flaws in it that are going to become very apparent in a flex break, showing ultimately lower actual strength than it's really there. The other weird thing about flexural beams is that you really have to keep them wet, really even through the moment of actually testing, because they're very susceptible to drying out, and drying out causes micro cracks, and micro cracks will potentially cause the beam to break sooner than it really should, and end up giving errors in what the actual true strength of the concrete is. We're seeing that more prevalent in low carbon mixes, which then themselves are a new animal on the market, and we're having a lot of problem with seeing flex beams come up to standard, even though when we do a core sample, we know that the strength of that sample is still meeting the actual strength of the structure. And not to mention that beams are cumbersome to transport. They're heavy. A beam is going to weigh somewhere between 60 to 80 pounds compared to a 4x8 cylinder, which is 8 pounds. So movement is much more cumbersome. And the types of aggregate that you use also, and the choice of that makes significant differences in that flexural strength. So all of these things add up to saying that if you had to use compression braking, then cylinder braking gives you more advantage today than flexural. And that's one of the reasons why we see it going away. Now compare that to using compression braking to or any type of braking to our Rebel sensor system. What's the difference there? Well, if you look at the traditional braking, whether you're doing flex or beams, cylinders or beams, you're going to have to test it in a periodic method. It's not real time. Cylinders are tested usually by standard 1, 3, 7, 14, and 28 days, and usually do 2 to 3 cylinders, crush those, average their number together to give you the strength at that particular time. And if you miss your target strength by even a day, at 1 day break, if you didn't hit your target strength, you gotta wait for 3 days. If you miss it at 3, you have to wait to 7. So it becomes very inefficient. Getting real-time data is the best way to go, and our Rebel sensor gives you real-time strength going the distance as long as you need it to be recording it. 28 days, 56 days. It really is a great product for giving you real-time strength as that strength is developed. Also, we have the ability to notify and tell you as a user when you've reached a particular strength. We also have the ability to predict what the strength is after a couple days. So all those things add up to improving efficiency and accuracy of knowing when you have to do your next operations or if you're meeting the final specified strength. Benefits of knowing strength in real time. If you look at horizontal, we can accelerate traffic release. We can enable early payment if you've hit the structures. A lot of horizontal work is paid when you reach the specified strength. So if you know when you've reached that strength, you can get paid. Vertical, we believe that our sensor system can save contractors about 50% of the cost of doing cylinder breaks. In slabs, along with the temperature that we produce, we show the user, you could increase the flexural, the strength of it. We also present our data not only in compressive strength but also in flexural strength. So using our sensor system with a slab gives someone some great benefits to knowing what that flexural strength is. Tilt up, again, very important to know when you can tilt up a slab and not have it crack or break. So early lifting is possible. Geotech houses can improve their labor efficiency from not making as many cylinders and managing the data that comes from the Rebel system. Ready mix producers can have a way to validate the mix design that they're delivering to their customers, and it'd be a way of certifying that and comparing it in case there was some differences between the placement and what was made at the plant. We already mentioned precast, the ability to remove the forms in a timely manner and then move those precasts around the factory without having them shatter. And, introducing the product internationally, we only produce a small amount of the concrete that's produced worldwide. Everybody in the world has the same problems we're talking about. So how does the Rebel system actually work? We're using piezo technology that creates a wave that we push into the concrete. And as the concrete gets stiffer, we measure the resistance of that wave going into that concrete. And as a graphical representation, if we look at on the left in this chart, or the left, you can actually see that wave as it changes in frequency. We push into the concrete a wave, a series of waves starting at 0 up to 200,000 hertz in steps of about 500 hertz. And when we reach a point of resonant frequency, the resonance of that, you can see that wave right around 60,000 or 60 kilohertz. It explodes, just gets its resistance is the weakest point of that wave, and that lower resistance is equivalent to the resonant frequency of that structure. Now, the interesting thing about resonant frequency is that resonant frequency is proportional to the dynamic modulus of the material. And a graphical representation on the right over frequency shows that as that resistance reaches its lowest point, you can see it peak at around 60,000 hertz. Very, very fascinating. And what can we do with that? Well, the great thing about resonant frequency and the dynamic modulus is that it is also proportional to the compressive strength. So if we can know the resonant frequency, we can figure out the modulus. From the modulus, we can determine the compressive strength, all doing this non-destructively. And as the concrete gets stiffer, we can see in this graphical representation, we can see that the compressive strength grows from 100 psi up to 2000 psi just by measuring that resonant frequency. And that's the basis of our patented process. How do we actually deploy it? Very easy. The sensors themselves are just either placed on the ground and the concrete is rolled over it, or the sensors could be connected to the rebar and concrete placed over that. As soon as the concrete is sensed by the sensor being placed over it, then it starts recording and generating strength. If you look at the system as a whole, it's a combination of just a sensor with a 16-foot cable that can be extended up to 100 feet. Inside that sensor has a piezo wave generator and a temperature probe. So we're not only measuring strength, but we're also measuring the temperature in situ, inside the concrete. That sensor is connected via plug into the data logger. The data logger has an impedance meter in it, a GPS location chip, so we know exactly where that sensor is located. A cellular radio that connects up to the web and transmits the data from the sensor into our database. Each data logger has a lithium-ion battery capable of going up to 28 days. It's wirelessly recharged in a cradle. The case itself is completely sealed. It can work underwater. It's very durable to withstand most of the environmental pressures. If we look at the whole system as a whole, you go from the construction site where the sensors are. The data loggers are communicating through the LTE cellular network. Data is not stored in the sensor. It is immediately, once it's measured from the sensor, it's sent up to the cloud for storage. We have an algorithm that works on that data, and that algorithm converts the sensor information to strength and temperature, and then it's presented on an easy-to-use interface that users could see immediately on their cell phone or on a tablet or at their desk with a computer. A closer look at what our dashboard interface looks like. It's pretty straightforward. It has a graph that shows both time and strength as it's developing. And if you have a set point, those set points are shown. If you have a set point, you're immediately notified once that strength hits that set point via a text or an email. And the other graph shows the temperature both in situ in red, so the temperature of the structure, and then the temperature that the data logger sees, which is the ambient temperature of the environment outside. So those three aspects of strength, real-time in structure temperature, and outside the structure temperature are all very powerful tools to help the contractors make decisions of what to do with their concrete, when they can do the next operation, when they can finalize and certify their strength. So as a total solution, the Rebel system is an embedded IoT sensor showing real-time strength. We use a machine learning algorithm to determine that strength. We do have an AASHTO standard. It's a standard developed by the DOT, T-412-24. That was just released at the end of July. And again, reviewing the benefits, we offer reliable real-time data, which allows contractors to potentially accelerate their construction schedules, reduce construction labor costs, potentially reduce cement usage when they know what their real strength is over time. They can eliminate the use of cylinder breaks, and all of this helps reduce the carbon footprint. That's a wrap for our session today in our Lunch and Learn. So appreciate you listening. If there's any questions, I'd like to open the floor up now for Laura to ask me some questions.
All right, thank you so much, Joe. We do have some questions coming in. First question is there specific information about the concrete mixture that needs to be provided to the databases?
Yeah, one of the things that we do with machine learning in our model is we like to know what the mix design is. So when you sign on and actually log in a sensor that's going to be used in a project, we do ask for the mix design. The mix design just gives us a basic water content, cement content, aggregate and sand, and then if there's any other types of additives. And it allows the model to know what type of structure we're dealing with. Is it a very fast curing concrete? Is it a slower curing concrete? And that just helps reduce our margin for error.
Gotcha. Okay, next question. Could you walk us through how the Rebel system integrates into a construction project? For example, what is the typical process for deploying the sensors on site?
We believe we have one of the easiest methodologies for implementing the sensor into a job site. Literally have to just put the sensor on the ground or connect it or attach it to rebar so it doesn't move around. It has legs so that it doesn't turbulate when concrete is poured over it. You bring the cable outside the structure, maybe put it through a hole in a form or put it in a hole through a bridge deck, and string the cable out. If there's something that's going to roll over the cable, then we suggest kind of creating a channel or a ditch where the cable can fall into. That's usually pretty easy on a job site. And then plug it into the data logger about 30 minutes before the concrete is going to be poured, and protect the data logger from being hit or run over by equipment. A lot of times it's placed under a cone or on a pole to get it out of the way to make sure that it isn't damaged. And as soon as you plug it in, it immediately starts connecting up to the internet via the cellular interface, and that's it. You can start looking on your phone and seeing the temperature, and as soon as the concrete is poured over the sensor, it will start gathering data. Now, it takes about 6 hours till we've gotten enough data and the concrete is stiff enough to start actually displaying concrete strength. if it's a normal cure or a slow curing concrete. If you have a fast curing concrete, then we start displaying the strength after an hour, and away you go.
Okay, thank you. Next question. In your comparison between the Rebel system and traditional cylinder or beam brakes, what has been the most surprising feedback from contractors or engineers regarding productivity improvements?
Well, it's really varied. I think first, contractors who've never used the Rebel system before are kind of amazed at how easy it is to deploy. And it's really kind of exciting when you're waiting for your first bit of strength to kind of show up. Then when you start seeing strength in real time and you don't have to do anything, that's really amazing because to date, if you're using compression braking or flex beam braking, you have to fill up the cylinders, you have to take them to a lab, then you have to wait on someone else to actually do the compression brakes, let's say if you're using cylinders, and report back to you. And there could be a time lag, somebody has to contact you. It's not where you get access to the data. And then you can start making your decisions. And if you needed to make a decision, a lot of times concrete is poured early in the morning or when you do the next operation, it might be the middle of the night. And maybe the technician that's doing your braking for you isn't going to be back in the office until early in the morning. So you lose a lot of time. So it's obviously when you know what your strength is in real time, you can develop your schedules and get people where they need to be and make the whole operation much more efficient.
All right, next question. Have the Rebel sensors been used at all for winter concrete? For instance, making sure the concrete doesn't freeze or if it can indicate if the concrete did freeze.
So the answer is yes. We've just released the Rebel product this year at the beginning of the year. So we're now just getting into the winter season. Of course, on some days when it's too cold that they don't pour concrete, but in a lot of vertical applications, they're pouring year round when it gets cold. And what they do is that they'll blanket or heat the structure when they're pouring the concrete. And so it's kind of important to know what the temperature is of your concrete when it's being poured and where it is in place. The beauty of the Rebel system is that we have a thermocouple in the sensor that will tell you what the temperature of the structure is. At the same time, we have a thermocouple that will tell you what the temperature is at the data logger outside. And it gives then the contractor some real-time feedback of what they have to do with the concrete to make sure that it doesn't freeze. And so a lot of times they'll put heater blankets on it and you get heated up and then you can see in real time the effect of maintaining the temperature of that concrete as it's curing. Now that's in the winter you had mentioned, but I'll mention in the summer as well, or in environments that get very hot, the opposite is true. Being able to see the temperature, and if it gets too hot, gives the contractor the ability to maybe cover the concrete or cool it down in certain ways. So not only strength is important, but temperature is important in so many different applications of the pouring of the concrete.
All right, thank you. Next question. Does the type of aggregate have to be known? For example, limestone versus granite.
So we talked about requesting what the mix design is, but our system is one of its beauties is that it's agnostic to the type of mix design. So it doesn't matter what type of aggregate is used. And also I should mention that we don't have to calibrate our systems. Some contractors have been using maturity sensors, which is nothing more than a thermocouple, and they try and compare that to the compression strength at a particular point in time based on its temperature. And that requires calibration, meaning that you have to do a test and calibrate the temperature curve to the strength curve and then correlate the two. And every time you change the aggregate, every time you change from one type of mix design to another one, you have to recalibrate. The Rebel system is agnostic to all of that because we're looking at the actual strength or structure or stiffness of the material. And the stiffness of the material is dictated by the type of aggregate. So if you change the aggregate from limestone to granite, you're going to be changing the ultimate stiffness or strength of that mix, and we're going to pick that up in the sensor. The resonant frequency is going to be different for limestone than it is for aggregate, and we will deliver a different strength, and that strength will be comparable to the type of aggregate that's used.
All right, next question. You mentioned a potential reduction in cement usage of up to 20%. Are there specific projects or case studies where the sustainability advantage has been realized and quantified?
Yeah, there's studies going on right now all over the country on ways to reduce the amount of cement or replace some of the cement in mixed designs. And cement is almost pound for pound equivalent to the amount of pounds of CO2 that it produces. So, and the reality is about 90%, but so it's a lot. So if you can reduce cement, you can reduce the carbon footprint of the concrete. So one of the things, the dirty little secrets in the industry are that because compression brakes and flex beam brakes tend to be inefficient and may deliver a lower than the normal strength if they're not prepared properly, the industry has been adding up to 25% more cement into the mix design to guarantee when they get to final strength and they do a compression brake, they can get paid. They can say that we've met the strength. What we have shown in our studies is that all too often the brakes are inaccurate and lower than what the actual structure is. And we're actually seeing that 20 to 25% greater strength because we have 20 to 25% greater cement in the mixed design. And so over time, if you use the Rebel system and you get some confidence level in what the true strength is, you can actually start to reduce the amount of cement and see the benefit of that in real time with our strength system.
All right, we have a few more questions here. With real-time tracking of concrete strength, how has the Rebel system impacted the ability to handle unexpected project delays, such as weather disruptions?
So it's weather is the enemy a lot of times of any type of contractor, especially when you get into winter months when you don't know how cold it's going to get and you know that you have to be doing something. So the compression brakes, let's say if we're doing cylinders, like I said, is an inexact science. You have to do them in a prescribed period of time. And when the environment gets bad, you can start to see that the concrete may not be curing at the rate that you normally expect. And so that causes delays on when you're going to schedule people. You got to get to a certain strength before you can do the next operation. The Rebel system allows you both to see what the strength is and how it's growing. And we also start predicting what's going to happen in the future. So if a contractor can see they're going to reach strength based on, at a particular time and knows that the weather is getting bad or wants to wait another day and to get to a particular strength, it helps them better plan around the weather. You can't do anything about the weather, but if you can know where your strength is going to be, you can better plan around it.
A fitting question for your first snow day. Okay, a couple more questions. How has the compliance with the T412-24 standard influenced adoption rates among departments of transportation or other regulatory bodies?
Yeah, that's a good question. Well, the DOT sets all of their standards and operations around their AASHTO specification that they've developed. So our first goal of getting an AASHTO test specification allows contractors to use our Rebel sensor in place of compression, cylinder brakes, flex beam brakes, and maturity sensors. And without that specification, they may not have been able to do that. On top of it, it's our system and our AASHTO standard is allowing DOTs to look at potentially using our Rebel system for final certification of strength and totally eliminating the need for either a cylinder brake or a beam brake for final spec. And so we're working in that goal, and a lot of the DOTs are both adopting our AASHTO standard to be used in construction with concrete, and looking to use it for final certification.
All right, thank you. So we just had another question come in. The AASHTO method does not mention using AI to estimate the strength. How does the user know that the AI model is reliable? This method does not mention using AI for strength estimation.
Yeah, that's a very good question. Well, one of it is usage. We have reams and reams of data that we share with our customers, with the DOT, with the governing bodies, that show our comparison of our model and how we develop strength to compression cylinder breaks. And so we can show very good correlation to the same degree that other test methods are. And a lot of times we're also verifying our methodology to core samples, which is kind of the gold standard, but not very often used, and used only when there typically is a problem. So the methodology that we use, if you go back to the scheme of our invention and our sensor, is that we're using wave propagation to actually determine the modulus of the material. And then from the modulus, then we calculate the compressive strength. The machine learning is a way to take all of the data that we're getting, and the data that comes out is a very complex waveform. And once you start using a frequency, you also start generating harmonics, and those harmonics have information in them. So the tremendous amount of information that is generated in just a sensor reading is immense. And so the AI model, or machine learning, if we want to call machine learning AI subset, is a way of taking a lot of data, millions of data points, and crunching them very, very quickly to come up with the true compression strength and do all the calculations that are necessary. So we've had great correlation. That's what we proved before we went to market with it. That's what we show our customers. And typically any customers who start to use our Rebel system will compare it to cylinder breaks to validate that the methodology that we're using is an accurate, reliable results.
Okay, great. Looks like we have one more question. Looking ahead, are there plans to expand the capabilities of the Rebel system, such as monitoring other material properties or further automating data analytics for project managers?
At the time right now, we're just focusing on strength and temperature, but as time goes on and what our customers are asking us to do, we may use it in other unique ways. Now, some of the unique ways that the system could be used in areas that have really no ability to give you good strength is things like rolled compressed concrete, RCC. It's a methodology right now that isn't, you're kind of rolling the concrete like you were applying asphalt, and there isn't a good method today. It's very, very hard to do a cylinder break with that because it's very low moisture, and you use compression to kind of give you the strength that you need. We believe that our Rebel sensor will be useful in those applications. Also, if you're doing something like a concrete overlay, which tends to be very thin, somewhere between 2 and 4 inches, it's hard to do a comparison with a compression break with that because it's very thin. Our sensor is only half an inch thick, so it's very useful to be able to be used in thin application areas like that. So more and more applications are being developed where the Rebel could fit a need that can't be done today with standard testing.
Awesome. Thank you so much, Joe, and thank you everybody for tuning in today. If you want to learn more, again, you can go ahead and scan that QR code on the screen, and we will see you in a few weeks. Thank you.
Thanks, everybody. Have a good day.